We're going to use ANOVA now for trying to determine the uncertainty which we can try and derive from different lot numbers of quality control. ANOVA, if you remember, is a means of quantifying the amount of variance between and within groups. So you can see in the example here on this spreadsheet, we have on the left here 3 different lot numbers for an arbitrary assay, all with reasonably similar results. As we would normally do, we would check for normality of the distribution of the results. We'll assume that that's the case. This is simulated data, so I've made it so it is normally distributed. So what we'll do first is we will do a walkthrough by hand to try and understand how variance applies to measurement uncertainty for a situation such as this. This is a common question that gets asked about how to approach it. So we have a series of measurements, lot 1, lot 2, lot 3. As we have done in previous courses, if I can press the right button, we'll just do some summary statistics. So we will count the number of samples that we've got. So we can see here, using the count function, we have 33 samples for each lot number, so that's a good start. That's one of the assumptions that we talked about in previous videos about equally balanced lot numbers of samples and numbers of measurements, so that's a good start. And one thing we need to do is to count the number of samples in total across all 3 numbers. So we just sum up the sum of each column there and we get a total of 99. Useful summary statistics are things like the mean. So we find the mean value here. The ANOVA is designed to test for differences in means taking variance into account. So we need that mean value for later calculations. And in addition, you can see here by averaging all the numbers between B2 and D34, we've taken what's called the grand mean, which is the overall mean of the overall distribution if we hadn't stratified it by lot number. K is the number of groups. So we can obviously see that we have 3 different lot numbers, so therefore we have 3 groups. And that's all we really need for the summary statistics at the moment. We could additionally do, of course, a standard deviation to try and work out standard uncertainties individually for each lot number for a comparison for the measurement uncertainty, but we won't do that at this moment in time. So if we remember, we are talking about variance. Variance is a measure of the distance of each data point away from the mean of each lot number of each group. So in the second table here, what we've done is we've gone through every value and measured what the distance from the mean is squared for each value. So in the first case, we're looking at the value of 23.7, looking how far away that is from 33, and in B38, which we can see down here, so the mean of 24.8. and then squaring it, and what that does for each and every single point gives us a measure of the squared distance of that point against the mean of that group. And we do that for each of the lot numbers, and quite simply by adding them all up. You remember with the capital sigma E-shaped symbol that we've discussed in the notations lecture, we add everything up so that all the squared distances between each measured point and the mean for each lot number is given in this sum column here. We then add up all of those 3 numbers to give us a sum of squares within. So these are the squared distances within each lot number added together, and then across lot numbers they're added together, and then we calculate an average based on what the numbers or what this sum value is, and also what the degrees of freedom is. And the degrees of freedom you'll see here is B37, which is our total number of samples, minus K, which is our number of groups, so in effect 96. And from there we have a mean sum of squares within of 3.898. Oops, press the wrong button again. So the sum of squares within gives us 1/2 of our root sum of squares equation for uncertainty based on ANOVA, so we can leave that value there. What we want to do now is to have a measure of the variance between the groups. So we start by calculating it for each group individually and then adding them together here. So if we look at this equation here, we're looking at B36, which is the number of samples within that group, N, which is 33, and then we multiply that by the square of B38 and B39. So that is over here. That is the difference of the group mean away from the grand mean. The grand mean, remember, being the mean of all three populations lumped into one group. So you take that mean away from that value, and in doing so, multiplying it by the number of samples used to generate that data, you get the mean sum of squares between the groups. I'll do that for group 2 and for group 3 as well, obviously using the respective mean for each group to make that calculation. Once that's done, you then add them up together to give a rather large total, and as we did before, we work out the mean sum of squares between by working out G43, which is the sum, divided by B40, which is the number of groups, minus 1 as our degrees of freedom. So that's K minus 1 on the denominator this time. In the case of ANOVA, we are looking at generating an F statistic. This is slightly different from what we saw in the F test. The F test, if you remember, was a measure of the variances of each group divided by each other. This time we're forming a ratio of the mean sum of squares between the groups divided by the mean sum of squares within the groups. So we can see that's 190 divided by 3.9ish. So that's going to be quite a large number. So that's 48.86. That's really high. And then we quantify, for doing any hypothesis test, we need to generate our degrees of freedom. So degrees of freedom 1 and degrees of freedom 2. And that allows us to calculate the critical value, as we mentioned in a previous lecture. So the degrees of freedom between is the number of groups minus 1. So that's K minus 1. And then the degrees of freedom within is the total number divided by the number minus the number of groups as well, so that's 96. Now that we've done that, we can use the F distribution using the degrees of freedom that we've calculated and the F statistic which we have generated from the ratio of our mean sum of squares between and within, and we can get a p-value, and we can see that that p-value is very, very small. And what that tells us, the ANOVA is a measure of difference in means, remember. And if we go back all the way across to our original descriptive statistics, we can see that there is a difference in means because lot 2 has a value for whatever these units are higher than the other two. Lot 1 and lot 3 are similar. Lot 2 is different. Bearing in mind, of course, that the ANOVA is measuring the difference in the means, taking into account the variance within and between each of those lot numbers. So even taking into account the variance, those individual sample distributions do not overlap and in effect come from the same population, so there is a difference. And for ANOVA, that's usually where you would stop. You would use ANOVA for measuring the difference in means between lot numbers, and that would tell us one thing. But what we can do is work out what our uncertainty may be based on these three lot numbers, based on how they've performed over a period of time. So we can work out what the uncertainty within the three groups are, and we do that by using the square root of G38, which is the mean sum of squares within. And you remember from the ANOVA output in the lecture, that's quite a simple equation to use based on the output of the ANOVA. So the square root of 3.9, or near enough, 3.9 is 1.97. And then we need to work out the uncertainty of the variance between the groups, which is slightly more complicated. If you remember, it's a conditional formula which uses either 0 or the difference between the between and the within divided by the number of samples, whichever is greater, and by within minus between, we can see that that is going to be greater than 0, so we use that. We take one away from the other and divide it by the number of samples in total, which is over here, 99, and take the square root of that to give us a result of 1.37. And finally, by doing the root sum of squares, so the sum of squares of those two values, G53 and G54, and square root it, gives us our overall uncertainty of 2.4 units. This is not in a percentage or anything, this is in whatever the units that these measurements are being made in, and that is what the uncertainty associated with the imprecision of the assays and the variance of the assays is a measure of that across the 3 different lot numbers. Hopefully this little demonstration has helped to solidify some of the concepts that we talked about in the ANOVA lecture. If it's not clear, then please put a comment in the comments below. But although it's interesting to see things done by hand and understand where the numbers are coming from, of course Excel will give you a more simple way of doing it. If we go into our data tab, ignore the warnings that come up, and go into our data analysis,